Our final speaker this morning is Dr. Charles Shanley, class of 1987. Dr. Shanley is Professor and Vice Dean for Clinical Affairs for the Wayne State University School of Medicine, President and CEO of the Wayne State University Physicians Group, and Professor of Surgery for Oakland University William Beaumont School of Medicine. Dr. Shanley will discuss the future of medicine, innovation, edification, and application. Welcome, Dr. Shanley.
Well, good morning. Thank you. It's really an honor. This is actually the second time that I've given one of these, and I'm more than just a little paranoid, because the last time I got to the second slide and we had a complete power outage. So my talk was a kind of a population-based study of the management of carotid artery occlusive disease, so it was full of statistics and all kinds of things like that. And it was difficult to do that without any slides, but we got through it. This one's, I think, a little bit more fun. It's really an extraordinary time in the history of our profession. And so I decided that I would speak to the future of medicine. A lot of these thoughts are my own, but some of them are captured in the epilogue of Dr. Larry Stevenson's book on the last 150 years. Has that been published yet, Sheila? It's coming out soon. There's an epilogue that Dr. Sobel, myself, and Don Weaver wrote, and some of the stuff will be in there. But I decided to focus on edification because edification speaks to more than just intellectual enhancement, but also moral enhancement. Innovation because it speaks to more than molecular discovery-based research or clinical research, but actually to the application of new knowledge. And application because we are in an era where technology is increasingly going to dominate medical care. That's not to say that the role of the physician as advocate and as partner and as manager and as the guardian of the welfare of patients will change, but the role of the physician as we've traditionally experienced it for most of us in this room is going to change rather dramatically. So in 1868, four Civil War era surgeons had a vision after their experiences in those dark days of improving the practice of medicine and improving education. And that vision manifested in the Detroit College of Medicine on Woodward Avenue and ultimately the Wayne State University School of Medicine. And over the next 150 years or so, and I know there was a talk on that earlier this morning, so I won't spend a lot of time, the contributions made by this School of Medicine to humanity are simply breathtaking. This, of course, is near and dear to my heart as a vascular surgeon, but Dodrell and Rippingill, there's a little bit, I say past as prologue, because just wait till the end here. But Dodrell and Rippingill really created modern cardiac surgery by, inventing together an engineer and a surgeon the first mechanical heart pump, cardiopulmonary bypass, and the first case done at Harper Hospital. Everybody, is aware of the contributions of Dr. Horowitz and the discovery of ACT, the first ray of hope in the battle against HIV/AIDS. I was a medical student when this article came out in Time magazine. I remember it and how proud I felt. But things change. I don't know if anybody knows the significance of these dates, but these are two papal inaugurations, one in 2005 and one in 2013, and something changed there. And all over the globe, everyone has a a personal electronic device of some sort or another. This change, the democratization of information, the democratization of knowledge is causing traditional hierarchies to tumble all over the globe, and especially in the practice of medicine. That democratization empowers patients. They are more informed, and we can't shy away from that. We need to embrace it because it is the future. And as care continues to disseminate away from the traditional hospital-based and hospital-centric model to a distributed ambulatory platform where patients will be making these diagnoses themselves in their own homes or at their own pharmacy, and in many cases the drugs that are specific to their physiome will be synthesized on site in real time, we need to embrace this and help them because technology is an enabler of change. But really, it's about cultural change, and the cultural change will occur not just with the patients, but with the physician community as well. Now, the explosion of information is a major driver, obviously, of the digital age. I like this graphic because it gives you an idea, with a kind of a size comparison as to just how much information is currently becoming available in our interconnected world. But the last one's the most important. 2/3 of the annual production of new information. You want me just to carry it? Oh. So I've got 2 microphones and it's still not enough. Is this any better? So 2/3 of the annual production of new information, by a size comparison, that's 1 exabyte of information, and that's about 2/3 of the new information that's produced in our country, in our world annually. So we have this phenomenon called the Internet of Things, which only promises to make that trend expand even more exponentially. It's estimated that by 2020 there will be 50 billion interconnected devices, not just smartphones, not just wearables, smart buildings, smart clothing, smart desktops, smart bathroom mirrors, smart automobile steering wheels, all of which can provide useful longitudinal, physiologic, biochemical, and other data that can be used to help inform the health of our patients and our treatments. Another megatrend that I think is having a profound effect and will have an increasingly profound effect, but also speaks to our relative lack of sophistication in medicine when compared to other industries, is the cloud computing architecture, which is only more recently seeing real application in medicine compared to other disciplines. And of course, all the big data approaches, the artificial narrow intelligence, deep learning, machine learning, and the things that have been so broadly applied in other industries are now just beginning to see application in healthcare. Richard Satava is a friend. He's a professor of surgery at the University of Washington, and he and I have done a number of things together for the American College of Surgeons over the years and the Department of Defense. He kind of coined this phrase, but I like it. Most of the innovations in the biointelligence age, which is where we are today, are occurring not in the traditional life sciences, but rather at the interfaces between the life sciences, the physical sciences, and the information sciences. Now, in a digital world, our edification, our education paradigms need to change in parallel, and they need to change rapidly. As a surgeon, I don't think you can ever replace gross anatomic dissection. However, in terms of learning anatomy, the ability to virtually manipulate the anatomy, to take organs and tissues out virtually from their in situ, to actually touch using augmented reality, the adjacent relationships, is something that is really profound and something that we need to embrace. Mixed augmented reality is something that we used. We had some funding from the Department of Defense and used that to look at laparoscopic skills training, and found that not only could we better measure proficiency using a combination of virtual and augmented reality technologies, but we actually could use augmented reality to coach faster assimilation of proficiency-based skills. And augmented and virtual reality are now being used with spatial three-dimensional data, CT, MRI, to do patient-specific rehearsals for complex extirpative procedures in cancer and other areas. So students need to become very familiar with these. They need to become familiar with them as medical students. They need to use them as medical students because they will increasingly dominate the way that they provide care as we move forward. Medical simulation is something that's near and dear to my heart. When I was at Beaumont, we started a medical simulation program, and we built a facility there with a lot of support from the community. At that time, it was one of the first 5 or 6 in the nation that was accredited. Now, I don't think you could find a medical school or a hospital that has significant GME programs that by mandate doesn't have a significant simulation. We think about simulation, to train team-based skills. We think about simulation to train, procedure-based technical skills. But simulation is being used to teach empathy, is being used to teach communication skills, is being used, as I mentioned, for patient-specific rehearsals and complex interventional procedures. So simulation is going to become part of the lexicon, not just of the educational paradigm, but also the practice of medicine. Gamification. A generation, actually now we're 2 generations, that grew up with gaming as a part and parcel of life. My brother and I were talking the other night, and we were talking about Netflix and how Netflix came to be. And he told me that, in my house, if I came home, my kids are all out of the house, but when I would come home, they'd be laying around watching stuff on TV, and they were really excited as more content became available. At his house, his children are anywhere from, first year in college down to, he's got one that's in 5th or 6th grade. They're all laying around on the couch, but they've all got their cell phone or something, and they're watching their preferred content individually. So it's really interesting. In games, anybody know what this game is? Farmville, right? So gaming, I never played Farmville. It's went from like one or 2 users on Facebook to 80 million users in less than a year. It became one of the most highly used internet game. But these things can teach situational awareness, team-based problem solving. You can measure proficiency and competency of a variety of cognitive and knowledge-based skills. These are things that the students of today embrace, they're used to, and they can rapidly accelerate the assimilation of knowledge. So in terms of innovation, the other thing we're seeing is an acceleration of the breakthrough innovations in medicine. Now this is like an embarrassing analysis because it's derived from data in Wikipedia. But if you look at the seminal breakthroughs by millennium, back through the time of Hippocrates, Galen, William Osler, who wrote his classic treatise, The Evolution of Modern Medicine, in 1921, and into what's now referred to as the postmodern era, you can see that the number of breakthroughs is accelerating dramatically. And that estimate of 1,400 is woefully inadequate because it's really just, amortization of what we've had since the turn of this century. I would predict that that bar would be through the roof in all actuality when we look back at the end of this. But what that says for the practicing physician, what it says for the student and for the resident, is that it's no longer going to be about rote memorization or even a simulation of a particular technical skill. We need to be teaching much more about accessing information, adjudicating it, and applying it, because there's not going to be any edification in rote memorization. The body of medical knowledge is increasing so rapidly, it's in such a rapid state of obsolescence, that attempts to memorize are going to be fraught with problems, because some of the things that we embrace today as principles will become outdated, perhaps within the course of a year, as we learn more and more at the cell and molecular level. Medical robotics, we think about it in surgery, but we've really only started to scratch the surface. And it's really macro robotics for certain invasive procedures, surgical robot for prostatectomy, various interventional platforms for cardiovascular disease, etc. But we haven't even begun to explore in any real detail the influence of nanorobots that could be swimming in the bloodstream, monitoring biochemical physiology and other types of changes, and the influence of robotics at the point of care. In Hungary, the pharmacies are managed this way. There's no longer somebody running around trying to find the pill and fill the bottle. Bionic medicine, it's no longer about a prosthesis. The prostheses now are, in some cases, better, stronger, faster. I mean, Steve Austin, the $6 million man, it's more than 6 million, but the sophistication, ocular implants, hearing implants, with wireless technologies to the visual and auditory cortex, it's really breathtaking, and the pace of change is only continuing to accelerate. When we speak about regenerative medicine, we're way beyond stem cell therapy now. We actually are growing bladders on biodegradable scaffolds that are then implanted. 3D bioprinters where the little ink jets are hydrogel, fibroblasts, myoblasts, and really functional liver architecture that's using for drug development and discovery, other specific organ structure that's being bioprinted and being utilized. Who knows what the future holds? Pharmacogenomics is obviously accelerating. We typically would just give drugs, pretty much the same dose to everybody based on weight or body mass. But, genetic polymorphisms, there was different levels of response, and we just accepted that. Some people didn't respond, most of them did, some had some bad side effects. We're now going to be able to use that kind of genetic information in real time, but not just nucleic acid. We can use lipidomic, proteomic, microbiomic, picturomic information in real time to design specific drugs. And when you couple that with cloud computing, artificial intelligence, now you can virtually test tens of thousands of molecules for specific, pathway-specific effects, and then use 3D printing technologies to print the drugs, perhaps even while the patient is at the pharmacy. Now, I know it's far out, but there's not much that we're talking about today that wasn't considered far out even a few years ago. Direct-to-consumer, we know about 23andMe, direct-to-consumer genetic testing, but you can have direct-to-consumer microbiome testing if you want to collect the specimen and send it in. Pretty much any body fluid could be tested, again, using a variety of sophisticated molecular genetic techniques. I was reading about, the gene editing technologies, and it's something, because my early part of my career, we had a significant focus on some of that molecular based research in my lab, but I read an article about somebody who ordered a CRISPR thing from an article in Scientific American and was doing some gene editing at home. So I thought that was interesting. Who knows where that goes? And who knows about the ethics of these things, really, right? I mean, it's kind of fascinating and frightening at the same time. Medical imaging and the influence of artificial intelligence we're beginning to see now, but I think this is a cute cartoon, right? I mean, what are the ethics if the computer algorithm makes a misdiagnosis? But increasingly straightforward interpretation of radiologic imaging, it will make sense that these AI platforms, which are much more sensitive, when they incorporate, computer vision technology, natural language processing, and a variety of other smart algorithm-based analysis, they'll be much better able to do the simple stuff. Whether they will be sophisticated enough to pick up on the rare things is a question. But AI platforms such as Molecular Sieve now, which do not only provide, the spatial imaging data, but actually really begin to characterize using AI type of algorithms for analysis the lesions and at least provide some prognostication as to the likelihood of malignancy, light years ahead of what we could do visually just at initial glance. This is really interesting. So this was just introduced last week. This is the Clara project from NVIDIA. And Clara is an interesting application of supercomputing, which they're using for spatial imaging data, but could certainly be used for digital pathology and any of a variety of other conditions. But basically, they can take digital data from they're agnostic to the imaging modality. They can use old, new, whatever. They take that data and using a variety of different algorithms, they can recreate three-dimensional models from that can be used for diagnosis, just from a standard ultrasound, 20 years old. And they showed this one where, this is kind of ultrasound, I think, with my children, I would get something like that. But through the supercomputing platform, they were able to render now that from that previous ultrasound data. So it's really just amazing what supercomputing can do and the applications that it will have. All of this can be applied to digital pathology, and there's a worldwide shortage of pathologists. So this is one of the ways that technology is going to solve that. But it could be applied to biochemical diagnosis, pretty much anything. The influence of trackables and wearables, Fitbit, but we're going to get to the point where there are implantables and wearables that are monitoring pretty much any function, any fluid in real time. And the medical Internet of Things, to parallel that is not just going to be limited to, patient-specific technologies to measure heart rate, blood pressure, and a variety of body fluids, but really every aspect of the healthcare delivery system will be connected, and that will allow a level of sophistication for population health studies that has really been unparalleled as we look at the influence of various interventions, treatment, risk modification on the health of patients and populations in real time. As individuals, we're going to have our own personal digital information system similar to a geographic information system where a digital record literally from birth that will include everything from who we've interacted with, how often we're out in the sun, really how many glasses of wine did you have last week, let alone our metabolome, our microbiome, epigenome, and everything else. It'll all be available. Blockchain technology is actually creating a level of trust and privacy that we can't have with paper-based records. And so this information is going to be available, and predictive algorithms will be developed that will help to identify risk factors as they develop over time and to encourage treatment. So we're in this postmodern area of digital health. There are a variety of different tools and technologies. I am not as sophisticated as I think I should be as a practicing physician. My son, who's a medical student, is so much more so, but there's a lot of the things in this digital health platform that he's not getting exposure to right now as a medical student, and yet they will, I think, increasingly dominate his practice life. So I wanted to take a second, and I think one of the reasons that I was invited to give this talk has to do with something that we've been doing in the Department of Surgery that is now, I'm hopeful, going to, within the next couple of years, have some benefit in human application, but has certainly had some benefit, I think, in terms of extramural funding to support research in the School of Medicine. In 2011, we began the process of moving the Smart Sensors and Integrated Microsystems program from the School of Engineering into the School of Medicine. It's now part of the Department of Surgery, part of the School of Medicine. And Greg Auner, who is the director of that program, is a physicist, computer scientist. I mean, he's really an amazing biologist and an amazing scientist. And he and I had collaborated on some other research, and we started an innovation platform to try to accelerate this translation from bench to bedside. And we've funded ourselves with a few other faculty members, just in a modest amount to get started. And the goal was to solve an important clinical problem in 5 years. So that was 2011. We did not achieve the goal, but we made some progress. And we thought that what is the biggest existential crisis that a technological solution could help with? And we determined that the problem of antimicrobial resistance and the problem of pandemics, specifically viral pandemics in a world of globalization, were problems that could not be solved without a technological solution. And the reason was that until we could say at the point of care, during the interface with the patient, what the heck was going on, behaviors would not change. Behaviors would not change, and this is where technology can enable behavioral change, but you still have to have the information. And all of our molecular diagnostics, any culture-based techniques, take at a minimum hours, but even then they have false positives and false negatives, and they're specific for one organism and not all organisms, and so they were a problem. And what we really needed was a technology that was agnostic to specimen, didn't have to be, go through extensive preparation, could be operated by an unsophisticated user, even the patient, that was reagentless, and that could make a real-time diagnosis or detect antibiotic resistance in real time. So these are a slide just outlining that diagnostic workflow, and there's a variety of different things, but the bottom line is you got the patient, and by the time the report comes back, the patient's already gone. So whether it's a viral pandemic that you're dealing with, Ebola, or whether you're trying to determine antimicrobial resistance and get the right antibiotic for the right patient, just not workable. So what we needed to do was somehow to create a technology that would allow that to occur in real time, and that was the stimulus behind the development of what we now refer to as Seraspec. Now, we leveraged a physical principle that's been known since the turn of the last century, which is Raman spectroscopy. When light is shined on anything, but if you use a single wavelength of light, especially with a very stable laser, most of the light is reflected back at the same wavelength, but a tiny fraction, about 1 in 10 billion photons, so a very tiny fraction, comes back and it's shifted slightly. And that shift gives extraordinary information about molecular structure, and not just molecular structure at a DNA, RNA level, but proteomic, lipidomic, and a variety of other structural things. So we reasoned, and Greg had some experience using traditional Raman technology, that if we had that kind of information, we could create a digital fingerprint that could be compared against a library of digital fingerprints, and we could develop a real-time diagnostic technology. And so, without going into any big detail, I mean, you can take a swab from a wound or a nasal swab, a rectal swab, put it in a little distilled water, nothing special, and then put it in and use these physical principles to make a diagnosis. And what happens when you do that and you use a Raman microscope, which is about the size of 2 of those tables together right now, and it takes about an hour and a half to get any information, but you'll get some data that'll spit out like this, and it's got information and peaks, and if you did MRSA versus MESA, if you did, E. coli, we've got H. flu, H1N1. We've developed these signatures for a lot of different organisms, but the bottom line is you get a lot of information, and every one of those little peaks means something, and you can tell strain-specific differences in organisms just on the basis of that molecular fingerprint. So I don't know if this is going to play. So this is the current iteration of it. You have the cuvette, you put your specimen, you put it in, press the button. These lasers are focused in on the specimen. They ultimately come in contact with individual organisms, and these Raman spectra are generated. The spectra are then, the quantitation is based on the intensity of the peaks, and within 100 milliseconds it can tell you what the organism is from an agnostic specimen. So it's really very exciting. I think if we can get it through FDA approval, it's a paradigm-shifting technology, because now you'll have a point-of-care diagnostic that you can come in with a sore throat and know that it's not, beta hemolytic strep, know that it's a virus. Our sensitivity and specificity data, the ROC curves and other things are near 99.9% statistical accuracy. Now, that's not doing, the FDA work that we need to do, but we have a lot of data, and it's very encouraging. But what's more important is, how are you going to fund things going forward? I sit on a study section at ARC, and we review 60 or 70 grants. 1 or 2 are scored to merit funding. It's been a few years since I've been on a basic science study section. I don't know, but that's a lot of work, right? And there's been a perception in medicine that, the funding from industry is somehow tainted or biased, but I think you can manage those kind of conflicts with disclosure. But just to give you an idea, last May 28th, we closed on an equity round of financing for this company. I'm no longer involved in the day-to-day management. I was one of the founders, but I'm on the board, but I'm not involved in the day-to-day. But to date, Wayne State has received about $3 million since, then in funding, direct and indirect funding for research. They'll receive more as we start a veterinary trial. Just last week or this week, Seraph signed a deal with a publicly traded veterinary pharmaceutical to use this technology in the veterinary space. And obviously the workflows are very similar, so it's even possible the FDA might take data in urine, for instance, and allow 510K approval from this veterinary trial, but Wayne State is going to receive licensing and royalty revenue from that. I would estimate another $4 million, and then if we get to the human thing, who knows what the value could be to the university of commercializing its intellectual capital. Universities in general are very good at protecting intellectual capital, not so good at commercializing it. Some are, but I think this is a huge opportunity for Wayne State. I think it's an exciting time. We've got a lot of brilliant scientists in the School of Medicine and on the main campus. They should be working with our clinicians, doing things like this. I think this is one of the ways that innovation is going to be funded in the future. So this is a quote from Jack Welch: "When the rate of change inside an institution is slower than the rate of change outside, watch out, the end is in sight." Okay? Now, I'm not done yet. I'm not suggesting that the end of medicine is in sight. I am suggesting, though, that these issues around digital literacy, okay, are something that we need to embrace. They've leveled the playing field. They've empowered the patients. They are going to lead to improvements in care that were unimaginable for most of us as we went through our training. And instead of fighting the tape, I think we need to get on board. So be prepared. Thank you.
Thank you, Dr. Shanley.
Oh, thank you.
Medicine.